10,
CLS, go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition, liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Every civilization, from the first humans who gazed up at the night sky to the modern physicists peering through their telescopes, has asked the same question: how far can we go? It is the question that humbles, terrifies, and inspires. The moon was once unthinkable. Mars was once unreachable. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Now, even the edges of our solar system feel small compared to the immensity beyond it. Because past the thin veil of our cosmic backyard lies the nearest great island of stars, the Andromeda Galaxy. A place so vast and distant that even light, racing at the fastest speed allowed by nature, takes over 2.5 million years to get there. And yet, we can see it with the naked eye. A smudge of ghostly light in the dark, teasing us with its impossible nearness. The universe's greatest illusion, visible but forever out of reach. For most of human history, the stars were gods, not destinations. We charted them, worshipped them, but never imagined crossing the void between them. Even today, with rockets, probes, and fusion dreams, that gulf remains absolute. When astronomers say Andromeda is 2.5 million light-years away, they are not describing distance in any human sense. They are describing a measurement that breaks language. Light-years are not a convenience. They are a warning, a reminder that the universe is too vast for our scale, too relentless for our timelines. If you were to leave Earth right now, aboard the fastest spacecraft ever built, the Parker Solar Probe, which moves at 430,000 miles per hour, you would reach Andromeda in roughly 6.6 trillion years. For context, the universe itself is only 13.8 billion years old. You could launch your ship today, let it sail until the stars burned out, and still you'd be barely 1/10 of the way there. By the time you arrived, galaxies would have drifted apart, stars extinguished, and everything you ever knew, the Earth, the Sun, even humanity, would be gone. You wouldn't be traveling through time, you'd be traveling out of it. And yet, we can't help but wonder, what if there was a way? Could warp drives, wormholes, or light-speed vessels make it possible? Could we outrun the limits of physics, or rewrite them? The temptation is ancient, to believe that distance is just another barrier waiting to fall. But the cosmos doesn't negotiate. Every kilometer you gain demands energy. Every acceleration bends reality closer to collapse. And the faster you go, the heavier the price becomes. Einstein didn't just describe a speed limit, he described a law of survival. At light speed, the world around you would distort. Stars ahead would blue shift into invisible radiation. Time would stretch, twist, and finally snap. For you, the traveler, seconds might pass. For everyone else, millennia. To reach Andromeda, you wouldn't just need a faster ship. You'd need a way to outrun time itself. And no civilization, no matter how advanced, has yet found a loophole around that. But imagine for a moment that we could. That humanity, somewhere in the far future, harnesses the energy to travel near the speed of light. That we launch a generation ship, a city of steel and starlight, carrying thousands of souls, and send it toward that distant spiral in the sky. The crew would be born, live, and die inside that vessel. Their descendants would inherit the same fate. 1,000 generations would pass before the first glimmer of Andromeda filled their viewports. To them, Earth would be myth. Home would be a memory stored in data archives. By the time their ship arrived, their DNA, their language, even their concept of humanity might be unrecognizable. This is not science fiction, it's arithmetic, because distance, on a cosmic scale, doesn't just separate space. It separates meaning. The farther you go, the less your starting point matters. The journey becomes an act of faith, not in reaching the destination, but in continuing at all. And that's what makes Andromeda so haunting. It is our nearest neighbor in the universe, and yet the distance is so monstrous that even light itself struggles to connect us. It sits there, calm, majestic, and patient, slowly moving closer. In about 4.5 billion years, our galaxies will collide, not through engines or ambition, but through the slow pull of gravity. What we cannot reach by will, the universe will bring to us by inevitability. So perhaps the real answer to the question, how long would it take us to reach Andromeda, is not measured in years, but in humility, because the universe is not waiting for us. It is moving, expanding, consuming, and transforming, indifferent to our desires. We look to Andromeda and see a destination. The universe looks back and sees nothing at all. The journey to Andromeda isn't just about distance, it's about scale and what it means to be small. We live in a cosmos so vast that even our imagination bends under its weight. And maybe, in trying to reach what we never can, we reveal the most human truth of all, that we were never meant to conquer the universe, only to wonder at it. Every species that's ever looked up at the sky has shared the same delusion, that speed is freedom. From the first hunter who sprinted after prey to the first pilot who broke the sound barrier, we've equated motion with mastery. But in the universe, motion is not liberation. It is confinement. Because the faster you move, the heavier you become. And the closer you get to the ultimate truth of physics, that the speed of light is not just fast, it's final. In the late 19th century, long before rockets, Einstein shattered the comforting simplicity of space and time. He revealed that they are not separate fabrics but threads woven into a single tapestry, space-time, and that speed pulls and warps that tapestry like a stone on a rubber sheet. At first, the implications seemed abstract. Who cares if clocks tick differently when you're moving fast? But as experiments confirmed relativity, as atomic clocks in jets began to drift by microseconds, as cosmic rays decayed slower than they should, the universe whispered a warning. The faster you go, the stranger time becomes. Let's say you build a ship that can reach 90% of light speed. You're not defying physics, you're paying its price. Your mass increases. Time slows for you, while the universe outside accelerates. At 99.9% of light speed, 1 year aboard your ship might equal centuries back on Earth. Push harder, and the equation becomes merciless. The energy required to move just a little faster rises exponentially. By the time you approach light speed, you're no longer talking about fuel or engines. You're talking about infinite energy, something no civilization, no matter how advanced, could ever possess. Because light speed isn't a frontier, it's a wall. And yet, this is where human imagination refuses to surrender. We don't see walls, we see challenges. If we can't accelerate to light speed, what if we could cheat it? Could we bend space instead of crossing it? Could we shrink the distance rather than fight it? That's the logic behind the theoretical warp drive. A bubble of space-time that carries a ship inside it, surfing the universe like a wave. Inside the bubble, you never break the speed of light. Outside, space itself does the moving. It's beautiful, elegant, and for now, impossible. Because even a theoretical warp drive demands energy equal to the mass of entire stars. The fabric of space-time may stretch, but it doesn't do it cheaply. You would need exotic matter, a form of energy with negative mass, something we've never observed, let alone controlled. And if you could build it, it might not just move you faster, it might erase you. The math suggests such a bubble could collapse violently, shredding anything inside. It's the universe's way of saying, you weren't invited to the gods' table. So perhaps the real limit is not technological, but philosophical. Because the laws of physics don't just stop us from traveling faster than light. They remind us of what we are. Creatures built from atoms that obey cosmic rules. We can twist them, exploit them, even weaponize them, but we can never transcend them. The speed of light, 299,792 kilometers per second, is not just a number. It is the dividing line between what is possible and what is divine. Still, humans are not wired for resignation. Every great boundary we've encountered, we've tested until it broke, or until we did. And that's what makes the idea of reaching Andromeda so haunting. Because it isn't just distance that stops us. It's the cost of speed itself. To move that fast, to bend that much time, would demand not just fuel, but sacrifice, the erasure of everything familiar, your loved ones, your planet, your era, all gone in the blink of your slowed eye. You could cross the stars and return home to find your homeworld buried under continents of dust, the oceans boiled away, the sun long dead. For you, the trip might feel like a few years. For the universe, it would be the end of time. And yet, inside that paradox lies something profoundly human. We chase the impossible not because we expect to win, but because the pursuit itself defines us. The same species that once feared crossing oceans now builds telescopes to see the edge of creation. The same minds that invented myths about the heavens now map them with mathematics. And the same urge that once drove us to climb mountains now drives us to imagine breaking the speed of light. We can't help it. We are built to reach, even for the unreachable. So how long would it take to reach Andromeda? At light speed, 2.5 million years. At our fastest, trillions. But the more honest answer is this. As long as we remain what we are, bound by physics, driven by wonder, and unable to accept that some horizons will never be crossed. Because the speed of light is more than a limit. It's a mirror. And when we stare into it, we don't see the end of the road. We see ourselves, small, defiant, and forever in motion. Imagine, for a moment, that all barriers melt away. That human ingenuity finds a path to near light speed. Not theoretical, not imagined, but real. A ship, sleek and shimmering, begins to slide through the void at velocities that approach the cosmic speed limit. At first, everything seems familiar. Stars streak slowly past. Instruments hum. But then, the universe begins to distort. And it is here, at the precipice of light, that reality itself starts to bend in ways that defy intuition. Einstein warned us long ago, as you approach light speed, time ceases to behave the way we know it. The faster you move, the slower you age, relative to the rest of the universe. It is not a quirk of clocks. It is not a trick of perception. It is reality itself stretching under velocity. A year aboard your ship might mean centuries back on Earth. Moments pass for you. Civilizations rise and crumble for them. You could leave as a child and return to a world where your birthplace is unrecognizable, your family long gone, and your species irrevocably changed. Space, too, begins to rebel. The stars ahead no longer shine softly. They become a blinding wash of blue light. The blues shift, radiation intensifying as photons pack closer together. The universe is no longer a vast emptiness, but a tunnel of lethal energy. Cosmic rays, invisible at rest, strike your hull like artillery shells. Shielding can protect flesh, but not imagination. The sky itself has become an enemy. And then there is length contraction. Distances shrink along the axis of motion. The Andromeda galaxy, 2.5 million light-years away, might appear compressed, a flattened blur stretching toward you like a cosmic ribbon. Yet this compression is deceptive. It does not reduce the energy needed. It does not make survival easier. It simply warps perception, a cruel optical illusion granted by the laws of physics. Traveling at light speed is not a journey. It is a negotiation with reality. Every acceleration, every push forward, demands exponentially more energy. The closer you get to the speed of light, the more the universe pushes back. Eventually, even photons, the particles that define the cosmic speed limit, seem to loom like obstacles rather than companions. And yet, for the observer inside, paradoxically, time seems to slow. A lifetime could pass on the ship while the cosmos around you ages beyond comprehension. Planets rotate, stars explode, galaxies collide, all in the blink of your subjective eye. This is why interstellar travel is not a matter of ambition. It is a matter of inevitability. Even if you harnessed infinite energy, even if you could survive the radiation, even if you solved every engineering problem, the universe will not wait. Civilizations rise and fall, suns burn out, and black holes scatter light into eternity. Your destination is not just far, it is hostile to existence itself. Yet, humanity imagines anyway. The thought of riding at light speed sparks visions of incredible beauty. Stars streaming past like diamonds, nebulae unfolding as ribbons of color across the hull. Andromeda looming ever larger, an entire galaxy stretching toward the viewport. The mind strains to process the scale, the distance, the audacity of being in motion on such a scale. This is what we chase. Not just the stars, but the act of daring to exist where few could survive. And here lies the cruel paradox. To travel at light speed is to move beyond human limits. But in doing so, you risk leaving humanity behind entirely. The traveler becomes a ghost in space-time. The universe moves on without them, uncaring, indifferent. The price of velocity is more than energy. It is isolation. It is the slow, unyielding awareness that every second you move forward, everything you know ages without you. So, how long to reach Andromeda at near light speed? Even if relativistic time dilation compresses subjective experience, the journey would still span lifetimes. Thousands of years for the crew, millions for those who remain on Earth. Your voyage becomes a meditation on existence itself, a contemplation of the fragility of life against the backdrop of eternal, indifferent space. Every photon you catch, every parsec you traverse, is a reminder. The universe is vast, relentless, and far older than our dreams. And in that vastness lies a question that will haunt every would-be traveler. Do we journey to reach a destination, or to confront the immensity of reality? Because at light speed, the line between the two disappears. We are no longer passengers. We are participants in the unyielding, unstoppable march of time and space. And Andromeda, patient and eternal, waits to teach us the cost of motion we can barely imagine. The Andromeda Galaxy waits patiently. It has always waited. It will continue to wait long after our sun has dimmed, long after the last atom of Earth has drifted into space. And yet, humanity dreams of crossing that gulf. Because if light speed is forbidden, there is another path. The generation ship. A self-contained world, a floating city of steel and biology, carrying hundreds, perhaps thousands, of souls across millions of years. It is a solution born from patience, persistence, and desperation. Imagine the ship's launch, engines ignite, and the vessel slides past the atmosphere, leaving behind a pale blue planet that will be nothing more than a memory for those aboard. Inside, life continues, but not as we know it. Parents raise children, knowing that they will die before the journey ends. Education is designed not for immediate use, but for a civilization stretched across centuries. Society becomes layered, a perpetual handoff between generations, each living for the survival of the species, not the self. And here begins the first truth of interstellar endurance. Psychology becomes as vital as propulsion. Humans are not built for isolation on this scale. Conflict, boredom, disease, and despair all threaten the mission. On Earth, communities thrive because they are embedded in a shared world, a known ecosystem, a familiar sky. A generation ship strips that away. The crew must create meaning in a controlled habitat, generating artificial ecologies, artificial cycles of life, artificial suns in windows that simulate day and night. Every failure in engineering or governance carries weight measured not in hours, but centuries. The ship's population must also maintain knowledge. Libraries, digital archives, and recorded instruction cannot be static. Generations of teachers must interpret and expand upon the work of their predecessors. Mistakes compound across centuries. A miscalculation in water recycling, or in genetic management, or in energy allocation could doom the mission long before the galaxy appears on the horizon. This is survival under extreme mathematics, the arithmetic of civilization in a vacuum. And yet life persists, because humans are stubborn, because even in isolation, we reproduce, we organize, we create. The generation ship becomes a mirror of Earth itself, shrunk to the confines of steel and radiation shielding. History repeats, not on continents, but in corridors. Political structures rise and fall. Religions emerge, evolve, fade. Children are born, they die, and the ship continues, a rolling testament to human resilience. But the journey imposes an unavoidable existential weight. Even if the ship functions perfectly, even if the descendants are healthy, educated, and aware of their mission, the Andromeda Galaxy is not a destination as we understand it. It is a concept, a point in space defined by coordinates, stars, and gravity, not a home. For those who arrive, Earth will be myth. The sun will be a story. Even our language, shaped by millions of years of drift, may be alien to the crew's descendants. The galaxy itself may have changed. Andromeda is approaching us, but imperceptibly. Stars burn, supernovae flare, black holes migrate. What they reach is a living, evolving structure, not the snapshot humanity envisioned. And this is where the lesson deepens. Distance is not the enemy. Time is. Because to reach Andromeda across generations is to reckon with evolution itself, of biology, culture, technology, and identity. You are no longer just planning a trip. You are orchestrating the survival of a species under conditions that Earth never prepared it for. Every decision ripples across millennia. Every error is magnified by the slow, relentless expansion of the universe. In essence, a generation ship is less a vehicle than a civilization compressed into a vessel. It is not enough to build the fastest engine. It is not enough to stockpile resources. You must engineer hope, the fragile, resilient hope that humans can persist, adapt, and thrive when nothing familiar remains. Because unlike a rocket race to Mars, the stakes here are absolute. Failure is not loss of mission or lives. Failure is extinction. And yet, even in this monumental challenge, there is something profoundly human. We are willing to sacrifice everything, lifetimes, identities, certainty, for the chance to touch a distant star, to look across the void and imagine that even if we cannot travel faster than light, we might still endure long enough to arrive. It is a vision of patience, courage, and defiance against a universe that does not care. So the question is not how fast we can go. It is whether we are willing to become time itself, a civilization in motion, carried across the darkness, bound together by purpose and discipline, facing a galaxy that waits silently, without concern, without recognition. In the end, the journey to Andromeda is less about reaching stars and more about proving that a species can survive the impossible. That in a cosmos defined by distance, light, and scale, humanity can still persist. Because even when light years stretch into millions, and even when generations replace generations, we keep moving. We endure. And somehow, that persistence becomes its own kind of triumph. To reach Andromeda, it is not enough to dream. It is not enough to imagine generation ships or warp bubbles or defiance of time itself. You must fuel the impossible, because distance is a trivial concern compared to energy, the currency of motion in a universe governed by immutable laws. And here, humanity faces its most unforgiving teacher, physics. Every spacecraft we have ever built relied on chemical rockets, explosions of fuel pushing metal through the void. It worked for the Moon. It worked for Mars. But Andromeda is not a neighboring planet. It is 2.5 million light-years away. To even approach a fraction of light speed with chemical fuel would require more energy than exists in the entire planet. Our most advanced engines could barely accelerate a single gram to a significant fraction of c. To move a generation ship, complete with thousands of humans, ecosystems, and life support, is beyond imagination. It is a scale our civilization has never approached and may never reach. Nuclear propulsion offers hope. Fission, fusion, even speculative antimatter engines. Each promises orders of magnitude more energy than chemical rockets. But orders of magnitude is not enough. To accelerate a vessel to 99.9% of light speed, the energy requirements grow exponentially. A single mistake in calculation, a single malfunction, could stop the mission before it leaves the solar system. The laws of energy are absolute. There are no shortcuts. Every joule counts. Every inefficiency is fatal. And energy is not just about propulsion. It is about life. A generation ship must sustain thousands of people for millennia. Food, water, air, all recycled in closed loops. Every kilowatt of power sustains ecosystems. Every watt matters. If the ship's power fails, humanity fails. There is no resupply, no rescue, no backup beyond the vessel itself. The voyage is total isolation. You are a civilization in a box, and every system must work perfectly for millions of years. And then there is radiation. Space is filled with invisible bullets, cosmic rays, high-energy protons, gamma bursts, all lethal to unshielded life. At near-light speed, even ordinary starlight transforms into deadly X-rays. Your ship is no longer cruising past stars. It is barreling through a wall of energy. Every surface, every material must be designed to absorb, deflect, or survive bombardment. A breach is not just dangerous, it is catastrophic. It ends generations. Even gravity becomes a problem. Humans are fragile. Centuries in zero-G atrophy muscles, weaken bones, disrupt circulation. Artificial gravity solutions, spinning habitats, centripetal force work in principle, but maintaining them across a vessel the size of a small city, powered for millions of years, is engineering on a scale never attempted. And these systems must be redundant, fail-safe, and almost eternal. The margin for error is effectively zero. Then comes navigation. In the vacuum of intergalactic space, there are no roads, no signs, no GPS satellites. The ship must rely on stellar maps, pulsars, and the faint signals of distant galaxies to chart a course. Errors compound over centuries. A deviation of a fraction of a degree early in the voyage could result in missing Andromeda entirely. You are not just traveling through space, you are threading a needle across a million light-year tapestry. And yet, even with infinite energy, perfect shielding, and flawless engineering, there is a final barrier. The universe itself is moving. Andromeda is approaching at roughly 110 kilometers per second, a cosmic dance of gravity and momentum. Stars orbit, clusters drift, interstellar gas clouds swirl. By the time a ship arrives, the galaxy will not be where it was when the voyage began. It will have shifted, changed, evolved. You will reach Andromeda, and it will not be the Andromeda your ancestors imagined. It will be a living, moving, unknowable world. The lesson is stark. Energy is the great gatekeeper. No dream, no ambition, no willpower can bypass the laws that govern mass, speed, and radiation. To traverse 2.5 million light-years is not just a journey. It is an act of cosmic negotiation, a reckoning with the immensity of the universe and the limits of human ingenuity. And yet, humans imagine anyway. We have launched probes beyond the solar system, built engines that defy imagination, and even today contemplate fusion and antimatter drives. We measure the cost in joules, terawatts, and exajoules, knowing full well that the numbers dwarf our current capabilities. And still, the mind persists. Because energy is a limit, but imagination is boundless. We may never cross to Andromeda, but the act of planning the impossible, of calculating, measuring, and dreaming, is itself a kind of triumph. The universe whispers through these numbers. You are small. You are finite. You cannot outrun the laws that govern everything. And yet we build rockets, spin engines, design cities for the stars. Because even in the face of an insurmountable energy barrier, humanity refuses to stop. And that defiance, measured in joules and ambition, is the first step across a void that no physics can yet bridge. The void is silent. It seems empty. But that emptiness is a trap. Because intergalactic space is not nothing. It is a field of dangers that laugh at human ingenuity, waiting to punish the unwary, the unprepared, the overconfident. To reach Andromeda is not merely to cover distance. It is to survive a universe designed to break everything that travels through it. The first danger is subtle. Interstellar gas and dust. Space is mostly a vacuum, yes. But scattered throughout the void are tiny particles, remnants of exploded stars, drifting at thousands of kilometers per second. Alone, they are harmless. But at near light speed, a single microscopic grain becomes a projectile with the force of a bomb. It can pierce hulls, destroy shielding, and ignite catastrophic chain reactions. Your ship may be a fortress of steel and carbon composites, yet even the smallest impact carries unimaginable energy. At these velocities, the universe itself becomes a minefield. Then there are micrometeoroids, fragments of asteroids, comets, and celestial collisions. These are larger than dust, but smaller than planets, often invisible to sensors. Hit one at near light speed, and the resulting explosion is enough to obliterate entire sections of a vessel. Shielding against this is not trivial. Thick armor adds mass, which requires more energy to accelerate. Deflection systems demand precision beyond anything humans have ever built. The faster you move, the deadlier these threats become. Every particle is amplified by velocity, and every mistake can end generations of planning in an instant. Radiation, too, becomes a silent predator. Even the faint light of distant stars, when encountered at relativistic speeds, transforms into deadly X-rays and gamma rays. Cosmic rays, high-energy protons and atomic nuclei moving at near-light speed, bombard the ship relentlessly. On Earth, our atmosphere and magnetic field protect us. In intergalactic space, there is no shield. Artificial shielding must absorb or deflect this torrent, or life aboard will succumb to cancer, genetic mutations, or acute radiation sickness. And shielding adds weight, and weight demands more energy. And energy, as we have learned, is already the universe's strictest limit. Gravity is not an ally. Stars, black holes, rogue planets, they are all moving through the void, sometimes predictably, sometimes not. A miscalculation in trajectory could bring your ship too close to a massive body. Tidal forces stretch and compress everything in their grip. Collisions, even glancing ones, release energies that make your engines feel like toys. Navigating the void is like threading a needle through a storm of invisible cannons. And yet, the most insidious danger is time itself. Because the universe is not static. Galaxies move, stars die, clouds of gas drift. By the time a ship has traveled a fraction of the distance, the landscape has already shifted. Planets form and collapse. Radiation storms erupt without warning. A path that seemed safe when plotted centuries ago may become lethal by the time the crew reaches it. Space is alive, slow, invisible, and unforgiving. It does not wait. It does not forgive.